Hello, and thank you for watching this Hexagon Geospatial e-training module, Automatic Terrain Extraction with Dense Point Matching. In this module, we'll see the prerequisites for automatic terrain extraction, see the interface for the dense point matching algorithm, and understand the settings and options to optimize your output DTM accuracy. The Automatic Terrain Extraction module has three algorithms available: Sparse Matching, ATE, Dense Matching, eATE, and Semi-Global Matching, or SGM. Before running any of the terrain extraction algorithms, a block file must be created and triangulation accepted. A block file contains raw imagery and all information needed to run triangulation, including imagery, camera or sensor information, ground control when needed, and elevation data. By running triangulation, a model is created to define the relationship between the images and the ground space. Terrain extraction cannot take place until triangulation is complete. I can check my triangulation results by clicking Block Triangulation on the Photogrammetry tab. The summary opens and I can see the value for the total image unit weight RMSE. This value is an indication of the block accuracy and whenever possible should be kept under a value of 1. With raw imagery, this tells me the accuracy will be within 1 image pixel. In this case, the value is 0.1037, well under a value of 1. If I haven't already done so, I would click Accept and Update. In this example, that's already been done, so I'll click Close. To launch the dense point matching algorithm from the terrain group on the Photogrammetry tab, I'll select Generate, Enhanced ATE, eATE, and click Yes to the attention box to save any changes to my block. This is the eATE Manager. This interface has all the tools I need to extract my DTM. When I start, the images are loaded into the viewer as footprints. I'll start by fitting the images to the window by right-clicking in the viewer and selecting Fit Image to Window. To see the raster images, I can select all the images in the table and then add a check mark in the visible column for each image I would like to see, in this case all of them. Finally, along the top toolbar, I'll turn on the Display Raster tool. This will activate all images in the viewer. First, let's become familiar with this interface. Along the top, I have tools that allow me to modify my display, set preferences, and finally run the DTM extraction. On the left side, you'll find the Save and Open tools. Next are Viewing tools. With these tools, you can decide to view footprints, rasters, or different types of boundaries. They also include Zoom and Panning tools. On the right of this tool palette, you'll find the Process Engine settings. We'll see more of these in a few minutes. On the left, I have the Project pane. This pane allows me to define images, AOI regions, and set certain strategy parameters. The table at the bottom shows information about each category in the project pane. The information you see here will change based on the category that's selected. We'll become more familiar with these tools as we make our way through the workflow. The viewer shows the raw images oriented based on the triangulation results. Terrain extraction utilizes the parallax or relief displacement between images calculated during triangulation. It's this offset between the images that allows the software to extract the terrain value. I'll start setting my project preferences with the project pane. By expanding the images category, I can see all the images in this project. You can see more information about these images in the table, including file location, height and width, and sensor type. Next, I'll click on AOI. If I want to, I can limit the DTM extent by defining an AOI region. For example, I might only want to extract a DTM for the quarry in this imagery. By limiting the DTM extraction area, I can reduce the processing time while extracting the area I'm most interested in. I can open the region definition tools by clicking the icon from my toolbar. Using the tool palette, I can either define a saved AOI or use the tools to digitize a new one. In this example, I'll just click Close. Seed data provides a starting point for the extraction engine and can increase the accuracy of the output DTM. A surface, or existing DTM, break lines, or mask points from a block file can be used as seed data. By default, the software will use a global DEM as a seed source. Here, I'll also add mask points from a block file. I'll select Add, Mask Points from Block File, and in the File Chooser, I'll select this DMC 10 cm block and click OK. It's now added with the global DEM as a seed source. Below Seed Source, we can select Strategy to view the strategy parameters that have been set. We'll take a closer look at this in the Strategy Parameters dialog box. From the tool palette, I'll start by opening the Process Engine settings. The settings within this dialog box can have a significant impact on the extraction processing time. Stop at pyramid level defines which pyramid layers are used in the extraction process. The default defines pyramid layer 0. This tells the software to use all of the reduced resolution datasets available and will ensure your extracted data is as precise as possible. It will also take longer to process. By changing this value to a 1 or 2, your processing time will decrease, but it may also reduce the accuracy of your result. Whenever possible, it's best to leave this set to 0. Point sampling density can also decrease processing time, but again, it can affect the accuracy of the final output. The eATE algorithm is designed to do a pixel-by-pixel interrogation. Changing this value tells the software to skip pixels and only use every second, fourth, eighth, and so on. This setting can be determined by weighing your accuracy requirements against processing time. Pixel block size defines the number of pixels considered in the processing at any one time. If your imagery has fiducial marks, the fiducial mark offset setting will trim your imagery so the fiducial marks are not included in the final DTM. If you were to add a value of 10, a 10% border of excluded area would be removed from the output. The Formatting tab defines settings for the internal processing. If you want to produce an RGB encoded output, be sure there is a check mark next to the RGB encode setting. In the Radiometry tab, the gradient threshold can be adjusted if your imagery has poor contrast or fidelity. Increasing this value can help the software find match points across the imagery and improve the output results. The imagery in this example has nice contrast, so we'll leave the default setting. A radiometry layer can be created to visually see how well the radiometry is working when computing the terrain output. This is not necessary, but it can give insight into potential problem areas in your output DTM. I'll click OK, and next we'll look at the output settings. From the toolbar, I'll launch the Output Settings dialog box. From the General tab, I can use the File Chooser to define where I want the output file to be saved if it's not already defined. The min-z and max-z values are threshold values used to constrain the eATE results. All values outside of this range will be discarded. The units are displayed on the right. These values can be modified, and in most cases, the values are derived from the global DEM and any other seed source when being used. However, if you have an LSR project, the default values will be -50 and 750 meters. The default values can be changed in the eATE preferences. By activating the bounding box, you can clip the output DTM by defining corner coordinates, or use the button to activate the AOI tools and define an output boundary. This is much like the AOI tool we saw earlier. In the Output Files tab, you can define which file types to output. When running eATE, you have the option to output 3 different file types simultaneously: a LAS or point cloud, a grid file such as IMG, DTM, or DEM, or finally a TIN. All 3 types can be selected, or, as in this case, just one. Today, I'll turn off the raster and TIN options and only output a point cloud. The Split tab allows you to split the output file into multiple smaller files and provides a couple of different options to do this. I only want a single output file, so I'll leave this set to none. The Thin tab allows for thinning of the final output data. This can be useful in cases where a system performs slowly with a very large number of points in the output file. With today's processing power, this is usually not a problem, and the defaults are recommended. The Classification tab defines what will be classified and how the software will identify buildings and vegetation. The default values for building and vegetation parameters usually do a good job at finding these features and are a good place to start. In this case, I'll use the default values. In Classification to Keep, select the classification categories you'd like to see in the output. You can select individual values, or in this case, tell the software to keep all the values. I can now click OK to the output settings. Next, we'll look at strategy parameters. As a general rule, it's a good idea to leave most of the default values. These values have been determined by engineering to optimize results. However, in some cases, changing the interpolation settings can improve the results. The interpolation method will fill in areas of missing values with one of 3 options. Mean performs an averaging across values, region considers a smaller set of points when performing the interpolation, and spike applies specifically to remove extreme values. A smoothing filter is also available to aid in a more homogeneous output. The degree of smoothing selected is determined by what features are in your input imagery. Less filtering is recommended to maintain the integrity of your data, especially when the area contains hard-edge features such as buildings. Finally, if the project imagery has poor contrast, a check mark can be added next to low contrast to improve the output results. I'll click Close on the Strategy Manager and Yes to save the changes and overwrite the existing parameters. Finally, I'll click on the icon to produce the processing elements. By clicking this icon, a plus sign has been added to the processing elements in the project pane. By expanding this folder, you can see the configuration files that have been added. Each file defines an element boundary that can be distributed and processed across multiple processors, or by using Condor to access processing resources on computers on a network. Using distributed processing can greatly reduce project processing time. Selecting the CFG file on the project pane highlights the bounding element in the viewer. There are times when the bounding element may be very small or be very redundant with other bounding elements. In that case, it's okay to delete the configuration file to save processing resources. I'll now click the icon to open the Batch Command Editor. By clicking Submit, I can define how and when to process the project. I'll increase the simultaneous processes to 3 to use 3 system processors at the same time. In this case, all 3 configuration files will process simultaneously. I can also choose to process now or define the date and time when the system resources are more readily available and run the process then. Here, I'll leave Start Processing Now and click OK. Now let's view the outputs. Here we see the Output Last file loaded in the viewer. In the upper left, the color by can be changed. As default, the data is displayed as elevation. Using the drop-down menu, we can change this to classification to see the classification categories. Finally, I'll change the display to color by RGB. This option produces a point cloud display that looks very similar to the original imagery. From the 3D View group on the Point Cloud tab, I can select Show 3D to open the point cloud in a 3D viewer. In the 3D viewer, you can tilt and zoom in to get a better view of the features. As you continue to zoom in closer to the points, they can become harder to see. In the Display group, I can use the Point Size tool to increase the size of each point. This helps fill in the space between the points and can improve the image display. I can also use the options in the 3D View group to change my viewing mode. Selecting the Perspective mode changes the points so they look larger, filling in the space around the points so they appear more filled in. This is similar to increasing the point size. Triangle mode creates triangle facets between the points, filling in the gaps between the points completely, including the sides of buildings and cliff walls. Thank you for watching this e-training module from Hexagon Geospatial. For more e-training, visit hexagongeospatial.com/etraining.